Hello again, glad to see you're back. We're going to start talking about acids and bases today. This unit will have some calculations in it, and some of you will appreciate the math of it, but we'll also give you some descriptive chemistry about what makes something an acid or a base. So I'm looking at our calendar here for April 2020, and we're basically going to be starting here today on Tuesday the 14th, giving you some overview of what acids and bases are. Then tomorrow we'll get into how to do some calculations, pH calculations, and they'll give you more background. It'll be me explaining a lot of different things on Thursday and Friday, and then maybe even Monday discussing more titration. I've included additional um, videos for you on each day of the calendar, and that would be great for you to look at to kind of see. Chemistry is one of those subjects where it's hard just to pick up a book and read. You're welcome to read your book and see if that helps, but I think watching, sometimes having someone explain it, sometimes works the best. So I'm going to go ahead and get ready and open up our PowerPoint for today. So we're dealing with acids and bases. Now, when you think of acids and bases, we hear these terms, but we're not exactly sure what they mean. Now, uh, some big ideas that I want you to get when we're all done. You should have some idea. If somebody says, what makes something an acid? You should be able to answer that question. You should be able to understand what makes an acid dangerous. Why is it we're concerned about if we spill concentrated acid on our skin or our eyes? What's the problem with that? Um, we want to discuss a little bit the environmental issue of acid rain and why people are concerned about too much acidity in the environment, why that's a problem. And finally, maybe as a consumer, you buy shampoo or something that says pH balanced or deodorant. You have no idea what that really means. Well, we'll discuss that as well. In terms of broad concepts, we're going to deal with some definitions of what makes things acids or bases. We'll discuss the pH scale, acid rain. We'll learn the names of some common acids and common bases. Then we'll apply this idea called Le Chatelier's principle and how it relates to maintaining your blood pH. And then we'll get into, if time permits, some weak acid calculations that has something to do with pKa, and we'll discuss buffers as well, and indicators and titration, all of this fun stuff, okay? At the end, I've listed a bunch of things here. You can come back to this moment in the tape if you want to review or look at the PowerPoint presentation. I'm not going to read each of these to you at this moment. So there's lots of ways we can measure pH. In the center here, I've got a very nice electronic pH meter. You can see the numbers here. There's a number 0, 1, 2, 3, 4, all the way up to 14. And usually the pH scale goes from about 1 to 14. That's what you're going to see. There's also this little, what I would call it, a little electronic dipstick, where you simply, it's battery operated, you pull the little cap off and stick it in a solution to measure the pH. You have pH paper that you may have used in middle school. You have litmus paper that will identify something as an acid or a base. And then we have something called a universal indicator as well. It's a color change solution depending on the pH. So the pH scale measures acidity or basicity. Another term for basicity is alkalinity. Usually we'll talk about the alkalinity of a substance. And I know you're thinking, I've heard that term before, but where? Do you remember the alkaline metals and alkaline earth metals? Those would be the group 1 and group 2 elements on the periodic table. If you place any of those alkaline metals or alkaline earth metals in water, they will produce a pH of greater than 7, and that would make them bases or alkaline solutions. The pH scale is a logarithmic scale. That's going to be important to understand what that means, and I'll describe it here in a little bit. I made my scale go from 0 to 14. I made it actually expand beyond 14, and yes, you can have negative pHs, although these would be very, very concentrated acids. An acid is described as anything with a pH less than 7. A base is anything greater than 7. The colors I've chosen the pink for an acid and the blue for a base will help you also remember uh, the litmus paper. Litmus paper is a type of paper you tear off, you dip into a solution, and we can say red to blue is base. That means if you take a piece of red litmus paper or pink and you put it in a solution and it turns blue, you have a base. We could also say blue to red acid. Now it sounds like I've got a little bit of an accent when I say that, but if blue litmus paper turns red, then you have a solution that's an acid. Now if you take a red litmus paper and put it in solution and it maintains red, you're not sure if it's an acid. It could actually be neutral. So you need to actually take the blue litmus and put it in the same solution to see if it turns red. Now what happens if you put red litmus paper in bleach? Well, the answer is it turns white. And if you take blue litmus paper and put it in bleach, what does it do? Yeah, it also turns white. So litmus paper has limitations. Every instrument, every technique has a limitation. So you can't tell the pH of bleach using litmus paper. You'd have to use something else, maybe a pH meter. If something has a pH of 7, it's considered to be neutral. Now, a common misconception is if something is pH 7 is neutral, that it's safe to drink. Now, I could take and put poison in a solution and then add acid or base to get it to become a pH 7. So pH 7 simply means you have the same amount of acid and base in solution. It's not a gold standard of safety just knowing the pH of a solution. Now, as I mentioned earlier, pH is a logarithmic scale. We're going to learn the equation pH is equal to the opposite log of the hydrogen ion. Now, what a pH scale, if it's a factor of 10, that's what logarithmic means. If I were to compare pH of 5 versus 6, so 5 versus 6, 5 has 10 times more acid than 6. Now, if I were to compare, let's say, 3 to 5, 3 to 4 is 10, 4 to 5 is 10. 3 is not 20 times stronger. You don't add them up, you multiply them. So 10 times 10, pH 3 is 100 times more acidic than pH 5. Now between pH 8 and 13, which is more basic? No, it's not the 8, it's the 13. As you go farther to the edges, the higher number for bases or lower numbers for acids are more concentrated. So pH 8 is 100,000 times stronger base. pH 13 is than 8. So we go 10 times 10 is 100, times 10 is 1,000, times 10 is 10,000, times another 10, 100,000 times more basic. So who came up with this interesting pH scale? Well, he was a Danish gentleman called Søren Sørensen, and he was a brewer, and in the process of allowing beer to ferment, they realized if you let it ferment too long, it would get somewhat bitter, become too much alkaline. So he had to figure out a way to measure when the beer was done. And so that's where the pH scale originally came from. And as I mentioned earlier, acids have pHs less than 7, bases greater than 7, neutral is pH of 7. Every time we change a factor of 1 numerically, it's actually 10 times more acid. 5 is 10 times more acidic than 6, and 3 is 100 times more acidic than 5, and 13 is 100,000 times more basic than 8. Now, to give you some perspective on what does it mean to be a logarithmic scale, let's compare it to the Richter scale on earthquakes, And so on earthquakes, that's a logarithmic scale. I put a 1, a dot here. Now you can't see it because it's too small, but that would be equivalent to an earthquake of a 1 on the Richter scale. You wouldn't feel it. A geologist would feel it, they could report that, but it would not be noticeable to you. A 2 is 10 times bigger. Now you can start to see that little dot there. It's not very big. It's like getting hit by a little dust ball. I suppose if you were doing absolutely nothing, sitting absolutely still, you might be able to notice an earthquake of a 2, but I highly doubt that. Now if we get to a 3, now all of a sudden that's 100 times bigger than the 1, 10 times bigger than the 2. This is sort of somebody sitting in the back of a class with their little pen and a spitball, and you get hit in the back of the neck. Yeah, you're going to feel that. It's probably not going to knock you out of your chair, but an earthquake 3 probably is going to start to get some notice. Now, when we get to a 4, that's getting much, much bigger. That's actually going to do some damage. That's going to cause the ceiling tiles to shake in the room, maybe glasses to fall in the kitchen, and there'll be some damage. Probably not a lot of fatalities. It's not going to cause a lot of homes to fall down or anything such as that. When we get to a 5, now that's starting to get pretty powerful. An earthquake 5 can cause structural failure in buildings, and you will definitely notice a 5. That's enough. It can probably wake you from your sleep. If we get to a 6, I can guarantee you will not sleep through that, and buildings will be falling down. If you get to a 7, wow, that's a big, big, big earthquake. That's 100 times bigger than a 5. Okay. Now, there was one, it was maybe 8 or 10 years ago, I forget the year, and it would have been by Sri Lanka, and I believe it was the second largest earthquake ever registered on planet Earth. And I believe it was in the ballpark of a 9.2 on the Richter scale. And it killed hundreds of thousands of people, and it created tidal waves and tsunamis. The tidal waves were probably 60 to 100 feet tall, and they came inland, maybe close to a quarter mile, killing hundreds of thousands of people. So that's what the Richter scale is. It's a logarithmic scale. Now I think you have a better idea when I talk about the pH scale being logarithmic. Every time you change the number 1 on the pH scale, it's actually 10 times more acid or more base. So we can see the circles getting bigger. So if we're looking at acid initially, it's very light pink, very little acid. And as I go from left to right, the pink color gets darker, meaning the amount of acid increases in that case. And the bases would be just the opposite. So you've got acid. As the acid goes up, the base goes down. And as the acid goes down, the base goes up. And right where the two have an equal amount would be neutral, pH 7. That's what we're trying to see by these graphics. Now, I've got a graph coming up here from the bottom, and it's showing the log scale, the pH scale, how much concentration of H plus, and the pH that would be present. And what it's trying to say is when H plus is very high, see H plus is very high here, the OH is very low. And that would be a low pH. A pH is 0 or 1 or 2 or 3. As I move on the pH scale from left to right, as I move over here, now the OH concentration is going way up and the H plus is going down. So it's the ratio of protons, H plus, and hydroxide, OH, that determine the pH. Now mathematically, I've talked about this, I haven't shown you the equation. pH is equal to the opposite log of the hydrogen ion concentration. Okay? Now, if you have an equal concentration of H plus to OH, it's pH 7. All right, so what else can I tell you? Well, let's give you some basic information about what's the difference between an acid and a base. An acid has a pH less than 7. A base has a pH greater than 7. Acids taste sour. We generally like sour taste. Think about like sour candy or something. We like that stuff, lemons and limes and stuff. We like sour. Bitter is not a flavor that most people like. If you don't know what bitter tastes like, well, you could lick a bar of soap and you would figure out that you don't like bitter. Some people like really dark chocolate. I'm thinking like 85% cocoa. To me, that's really, really quite bitter. I like milk chocolate that's just not bitter that way, masked with sugar. Acids react with bases. Bases react with acids. We're going to define, one way to define an acid is it's a proton donor. In other words, acids donate or give away protons, where bases, they're the opposite of an acid, they will accept a proton. I mentioned that in litmus, we said blue to red acid. Blue litmus paper will turn red in an acid, where red litmus paper will turn blue in a base. When we're thinking about how much H plus and OH, if you have more H plus, that's an acid. If you have more OH, that's going to be a base. Reactive acids, react with metals, and bases, they don't generally react with metals. Both are electrolytes, and we'll have to discuss electrolytes a little bit later. But if you remember, electrolytes are ions that carry an electric charge. The fact that this is going to produce an H plus or an OH minus, it's making ions, so they will both be electrolytes. So let's summarize by discussing the difference using our double bubble mind map between acids and bases. They're similar in that they both can affect pH and litmus paper. They're related to the proton concentration in solution. Mathematically, we're going to learn this relationship that pH plus pOH always equals 14. Today's not really the math day. We'll add that to another day's discussion. Acids have a pH of less than 7, they have a sour taste, and they react with metals, whereas bases have a pH greater than 7, a bitter taste, and don't react with metals. So I've summarized those properties here for you. I've added some examples of everyday acids and everyday bases. Now this might surprise you that milk is considered an acid. On the pH scale, it is less than 7. Now it is much more basic than most of the foods that we consume, but nevertheless, it is still an acid. So here we go, some stuff on acids, and then some stuff on base, and I've given you a good graphic to think about acids. Think about a lemon or lemon juice, and a base, just a bar of soap. Another property of bases, and I didn't mention, bases tend to be slippery. Imagine, and you've done this before, you hold a bar of soap, you get it wet, it's a little bit slippery to the hand. Okay, that's a property of bases. I'm going to list some common acids and bases here, and then we'll probably keep this video pretty short today. So these are some strong acids. Hydrochloric acid. Hydrochloric acid would be, stomach acid. That's where you would probably be thinking about hydrochloric acid. Nitric acid. Nitric acid, HNO3, is another strong acid. Now, I haven't talked about this, but strong means that it dissociates fully or breaks down fully. We'll discuss that in much greater detail a little bit later. Perchloric acid is another strong acid, and sulfuric acid. Sulfuric acid is the most common selling acid in the world. A big use of it would be battery acid. There are 7 strong acids. I'm only asking you to know these 4. There are some strong bases: sodium hydroxide, potassium hydroxide, calcium hydroxide, and these also are strong electrolytes and dissociate fully. Weak acids don't dissociate fully. 2 that I'd like you to know: acetic acid, that's also known as vinegar, is a weak acid, and carbonic acid. Carbonic acid is how you would carbonate beverages like pop. If you ever go to the restaurant and you get a drink from the fountain, it's going to have carbonic acid mixed with a syrup, the flavor of Coca-Cola or whatever you're using. That's how they carbonate your beverage. A weak base I'd like you to know is ammonia. Now, ammonia doesn't look like it has an OH in it, but it actually does, because ammonia, when you buy it, is ammonium hydroxide. If you've been in my class, that's the stuff, if you have a plugged up nose, it has the green lid, I let you waft, and it smells horrible and clears you out. That's ammonia. What ammonium hydroxide is ammonia gas dissolved in water. So ammonium hydroxide is ammonia. They mean the same thing. All right. Finally, if we're looking at just basic classes of reactions, you're wondering, well, what happens if you take an acid and a base and put it together? Well, you get a salt plus water. This reaction is called a neutralization reaction. It's a type of double replacement reaction with formation of water as the driving force. Perhaps you wake up in the morning and you drink a glass of orange juice to get your day started, and then you have some cereal with milk in it, and it generally gives you a very bad taste. That's because when you have things such as an acid or base, they make salts that don't taste very good to us. Maybe you have an evergreen near the front of your house and you have concrete and it rains. If it's new construction, when it rains, concrete's very basic and it leaches out the hydroxide into the evergreen, and the bushes will actually turn yellow and then die. Perhaps it's springtime and you're putting a base fertilizer on your yard and you sprinkle it under a pine tree. Well, the base and the fertilizer and the pine needles that drop down to the ground, which are acidic, will make a white powder. That white powder is salt, and that will not be good for your pine trees. You are not going to get grass to grow under a pine tree no matter how much you fertilize it. It has nothing to do with not enough light. It has everything to do with the pH under the tree is acidic. Pine trees are one of the few plants that enjoy and like living in an acid environment. So let's look at this example at the bottom. I've got hydrochloric acid and sodium hydroxide, and what I'm going to do is a double replacement reaction where the hydrogen and sodium switch places, so the sodium ends up with a chlorine, that's table salt, and I'm left with an H with an OH, that's water. So what's happening is an acid plus a base makes salt plus water. All right, that's where we're going to stop today. We're going to continue our discussion with acid-base neutralization maybe tomorrow. So let's go back and, well, I think I'll just go ahead and stop this recording at this point, and we'll call this one done for the day. Let's see if we can do that. And so we're back here. So I'll say have a good night, and please go ahead and watch those videos as well on acids and bases. All right. There's one here where he's Dr. I don't remember what this guy's name is, Dr. Dave or whatever his name is. He's going to be talking about acids, what makes something acid. So go ahead and watch that video, get a little more background before we meet tomorrow. There's also a basic video on what makes an acid a base, a little bit shorter down here. And if you're curious to learn who invented the pH meter, it was actually somebody who lived in our area, who attended University High School. His name was Arnold Beckman. And so I left a little short biography on Arnold Beckman here for you if you wish. All right, have a great day and stay active and stay healthy.